I need an antenna for the 70 cm band, tuned to 437.5 MHz. So in this video, we're going to design and build a Yagi antenna, and then we will see how well the real-world results line up with the theory. The first challenge was simply figuring out which design numbers to trust. All the online calculators I tried gave me slightly different element lengths and spacings. I eventually settled on Alexander Frank's DL6WU-based calculator, mostly because his results agreed with Jeroen Steeman's calculator, so that became the recipe. The design is straightforward. The driven element is a straight dipole. 1 reflector, 5 directors, which should give us a gain of about 9+ dBs. For the boom, I'm using a 2-inch wide strip of plywood. The elements are 3mm brass rods. They are mounted with ABS brackets I designed in Fusion 360 and 3D printed. Cut the rods over size on the bandsaw. Grind them to final length on the disc sander. I marked the element positions on the boom and clamped them down with the printed brackets. A straight dipole is close to 50 ohms. So I'm using a 1:1 balloon between the feedline and the two dipole halves. I tack glue it in place. Solder the elements to the balloon leads. And then solder a short RG316 pigtail to the remaining terminals. That gives me a neat connector to the test gear and in the future to the transceiver. Now it's time to see what this thing actually does. To test the full sweep, I connect the antenna to the LiteVNA using a run-off KMR 240 coax cable. After full open, short, load calibration, I sweep the antenna. The results depend a bit on how I hold the boom and the cable, but the main points are: primary SWR minimum is about 1.65 at 428.6 MHz. The secondary SWR minimum is about 4.1 at 437.8 MHz. So the question is, did I build it wrong or is the recipe itself off? To answer that, I modeled the antenna in XNEC to C using the exact element lengths and spacings from the calculators. NEC treats each element as a thin wire in free space, so it's an idealized version of the antenna. No boom, no brackets, no balloon. But it's excellent for understanding trends. The model geometry is exactly what I had built. 1 reflector, 1 straight dipole-driven element, and 5 directors, all with 3mm wire diameter. Then I sweep the model from 400 to 450 MHz, and the results look like this. Simulated SWR minimum about 1.25 at 427.7 MHz. Simulated secondary minimum about 2.8 at 447.2 MHz. That lines up surprisingly well with the LiteVNA measurements. Both the real antenna and the NEC model agree that the antenna is happy around 428 MHz, not the promised 437.5 MHz. And it's the same story for the radiation patterns. At 428 MHz, the NEC patterns look great, strong forward gain, clean front to back ratio. But when you move up to 437.5 MHz, the pattern starts to distort and even get some gain in the opposite direction. So the antenna isn't just mistuned in SWR, it is mistuned in pattern performance as well. I modeled 3 calculator-based designs, and every one of them show the same thing. Their best behavior is between 428 and 430 MHz. None of them hit 437.5 MHz very well. So the calculators agree with each other and the measurements agree with the simulations, but they all miss the desired target frequency. Something in the design assumption, the DL6WU scaling, the element diameter corrections, or the way these calculators handle short boom Yagis is shifting the resonance downward. If you have any ideas, please leave me a comment. I'd love to understand what's going on here. For now, I might just mount this Yagi on the antenna rotator and see how it performs on real satellite passes. Stay tuned, thanks for watching, and see you next week.